and why we need some different kind of approach to solve this problem, right? So now, can you think of any approach to solve this? So forget about algorithm or design method. So if I ask you to solve this problem, how did you get this I4 and I2? Okay, this I3, I2, I1, I got it by applying the greedy approach. But if I ask you, how did you come to I4 and I2? What process you have done in your mind with help of which you have arrived to the conclusion that if I include I4 and I2, I get the maximum profit? So we will understand our thought process, and accordingly we will design an algorithm. So what we are trying to do is, the first attempt every time when we try to do is, the first attempt is to always try to convert our thought process into an algorithm. If it can be efficiently converted, then your algorithm design is done. If it is not, then we apply for some different methods. Okay, so Shreyans has said sack capacity. Okay, tried all possibility and picks the best one. First max price. Yeah. So based on our thought process, our natural thought process, the most obvious solution would be to try out various combinations and see if it is the best among that, right? So you might have looked at, see, some of you might have looked at the best profit. So the first one to choose should be something which has a higher profit to weight ratio, right? So you might have taken that and you might have added something. If the tally doesn't match, you might have backtracked, you might have changed your earlier decisions, you have once again you might have done. And some might have properly tried all the combinations, like you might have included I this one, then you have checked this, then you have checked this, then this. So you might have tried various combinations and you might have found out the best among that. So there could be multiple approaches to it. So that's the natural way of solving that. But when you want to have a proper algorithm designed for this, a proper set of algorithms for this, what you are supposed to do is, we have an approach called as recursive approach. Remember, it's very important to understand this recursive approach. Once you understand this recursive approach, then it would be quite easier for you to solve any dynamic programming problem. So here, when we try to approach this problem with a recursive approach, we will check the logic, and once we analyze that logic and once we code it into a program, for next subsequent problems, we will first make sure whether the same approach can be applied for other problems or not. So there are cases where we might not directly apply recursion, but we might apply some other methods. But what is that in a problem we always look for, where we decide that this problem has to be solved by recursion or some other method? So that we will slowly learn. But as of now, let us try to learn this approach for 0-1 knapsack. And this problem is basically same, and it applies for almost 10 to 15 other problems. Okay, so let us think of the basic approach. So what we will try to do is, we will check all possible combinations. That will be our approach, right? See, the most crude and most intuitive or the brute force approach which I can apply to get this is, see, here you have only 4 items you can do it for. For example, if I have 40 items such, can we apply everything in our mind? We cannot, because 40 means there could be a lot of combinations. So here it is 4. Some calculations are quite easy which you can do it in mind, so you are able to come to this answer. So let us look at that approach, how we will solve that. And once we have that approach, what we'll do is, we'll try to convert that into actual mm, algorithm, right? Okay. So far, any questions? Do you have any questions? Okay, so let me move to another screen. Okay, I hope you see this screen here. So now I have this table, right? What is this table? This is a table of my problem which I had in the earlier screen. 4 items. Each item has its profit to weight, profit weight, and the maximum sack capacity is 7. Okay, so this the sack capacity. And so let me have a small node. So this node indicates the problem I am trying to solve. So I am trying to solve a problem which has 4 items, I1 to I4, and current max capacity of my sack is equal to C. Here I am writing a general word, so I'm not including numbers, so I can generalize this for every other input. So I am saying C. So right now if you ask me what is value of C, C will be 7. And initially, before I solve this problem, what will be the profit value? Profit value will be 0. So as and when I keep on solving this entire problem, my profit will keep on increasing. So we will choose one such node in this diagram where the P will be maximum. That's my approach. So in short here, what we do is we apply this approach. Okay. So every time, whenever I want to include or whenever I want to solve this problem for any item, what I'll do is my objective here is to find max. Okay, you want to find max for all the items from 1 to 4, right? This is what I want to do here. So max of items 1 to 4 will be, how would you achieve this max of items for 1 to 4? So I want to find out max of 1 to 4 for all I from 1 to 4. Okay. So if you want to calculate the maximum profit for items from I1 to I4, let me increase the font. Okay. So there are two possibilities. What is that possibility? Calculate the price, calculate the profit by considering by involving I1 in the solution, or there could be another case for that. Ignore I1 and try to find out maximum of this. So there are always two possibilities. I might get the maximum profit by including item I1, or I might get the maximum profit by excluding I1. Right. So I have these two possibilities. Likewise, when I come to I2, I might get maximum profit after including I2 or even excluding I2 as well. For example, if you look at the earlier screen, so here you will understand that. So when you look here, initially you have applied I4, but you have ignored I3. Why you ignored I3? Because you couldn't include that. So if you look at the solution vector here, the solution vector looks almost similar. Did I include I1? No, so I1 will be 0. Did I include I2 here? Yes. So it is 1. Did I include I3? No. Did I include I4? Yes. So this is how the solution vectors look for this problem. And this is called as solution vector, and we represent this inclusion or exclusion by either writing 0, 1 or 0, 1. Right. So what I'm looking is, so here I got maximum profit by excluding I1. So there could be some problem where I might get maximum problem by including I1. So every element here has two decisions to be taken. What is the decision? Either to include that element or to exclude that element. Fine. So if that is the case, if I want to solve a problem with item I1 to I4 m is equal to C, I have two possible cases. So I will get max. See, max of this could be written as, for example, let me is equal to, this can be written as max of I1 to 4 can be written as max of I2 to 4. So here I write 2 to 4. And see, for items I to 4 and M, the cap capacity, the maximum sack capacity M is equal to C. Okay, so let us represent the problem as this. So if I write it this way, max of 1 to 4 is equal to the profit associated with that. So let us call it as profit associated with I1 as P of, let us call it as P1. So P1 plus, if I include profit of this, if I include the first item, the next problem will be from I2 to I4. And what will be the sack capacity if I include the first element? If I include the first element, the sack capacity will be M is equal to C minus W1, right? So why do I write W1 here? So let me make it clear. Okay. So either P1 plus P1, the profit of first including either of this, you will get a maximum profit from this, or maximum of two values. If I completely ignore, if I completely exclude item 1, what will be the next problem to solve? Same, the next problem will be 2 to 4. Next problem will be still from 2 to 4. But since I have decided not to include item 1, my sack capacity still remains the same. Okay, so that's how we solve this. So this is max of this term. Let me make this in and max of this term. Max of these two terms will give me a profit for these two items. Okay, right. So if you further expand this, what is further expansion? You have to expand this max term and you have to expand this max term. And when you keep on expanding, it will grow like a tree, right? So I want to solve this, right, from 2 to 4. So here I have two elements, two possibilities: include I2 or exclude I2 with this weight capacity. Here too I have two possibilities: include I2 or exclude I2. If I include I2, then I have to solve from I3 to I4. Then I have two more further choice to be made: include I3 or exclude I3. Then further, then I4, include or exclude. So this problem goes like a recursion. So let us see, that approach would be far more clear when I start drawing the tree. So if this is a problem, this problem is divided into two sub problems. What is that sub problem? The first sub problem is this, and the second sub problem is this. So what we will do is we shall represent the second left side of this to include element, and we will include right side to represent exclusion of element I2, right? So this will represent, this block will represent a sub problem which includes I1. This sub problem represents a sub problem which excludes I1. For this sub problem, if I include I1, what is the next remaining sub problem to be solved? From I2, I3, I4. Since I have included I1 in this, what will be the new sack capacity for this? C minus W1. And what will be profit at this point? It would be P1, right? And here, since I have decided to exclude I1, neither the sack capacity changes nor the profit changes. So I have completely ignored I1, because maybe I1 can't be included in sack due to the weight of I1 being higher than that. Okay, so don't look at this problem. I'm talking in general here, right? So now this node has two more decisions. Can you tell me what this will have? So this will have two more solutions. So okay, what is that? Okay, So when you solve this, what this will have, left side includes inclusion, right side includes exclusion. So the new subproblem to solve will be for I3 to I4. Since you have included I2 here, what will be the new sack capacity? W2. You will include this W2, and profit will be P1 plus P2. And this will include, you have to solve it for I3, then the weight remains same and profit remains same. So what this node is telling you? It is telling you a sub problem which was arrived by including I1 and excluding I2. So here you have to solve this sub problem. What is this sub problem? Find max profit with items I3 and I4 in your input with sack capacity C minus W1 and current profit as P1. So whatever further you do, it will add to P1, right? And now this node will have two more combinations. Okay, so can you tell me what this node will have? This node will have two more combinations here. So let me do it for one branch, then you will understand. So this is I3 and I4. When you're solving for this problem, you have two choices, either to include I3 or either to exclude I3. If you include I3, what will be this next problem to solve? I4 with sack capacity as C minus W1, W2, W3 and profit as P1 plus P3. And this for I4 and it remains same. So excluding I3. So it is include I1, include I2, then exclude I3. This remains the problem for that. So you will solve for this. So if I further solve, this has two more sub solutions. What are those? These are the two solutions for this. So this indicates, left side indicates inclusion. Okay, so what you are solving this for? You are solving this for I4. Then when you're solving for this problem, your input no longer appears here. You are no longer considering, and there is no element to consider here because you have exhausted all I1, I4. So I4, include I4. If you include I4, what will be the sack capacity? Minus W4. And what will be profit? P1 plus P4. And here, if you decide not to include I4, the profit will be same as that. What it is? C minus W1, W2, and this is. So what is this vector denoting? Including I1, include I2, I3, and when you're coming for I4, exclude I4. So what is this denoting? It's denoting a choice decision sequence where you have decided to include all items in your stack. Now the solution changes this way. It is our final decision whether to include this solution in my solution vector or not. So when you will include this solution vector, if this M, this sack capacity and whatever you have included, this is within a valid range. See, if you include C minus W1, W2 and W, if you get M is equal to -1, it means that probably the sum of all these weights is exceeding the sack capacity. Does it make any sense to include such? No, we do not include any such solution whose combination, whose addition of weights exceeds the sack capacity. So what will be profit here? Profit will be P1 to P4. And if M becomes negative, I entirely ignore this one. If M is positive, means I am well within the capacity of knapsack and I can now consider this solution. Likewise, we generate lot more other solution to this. For example, I have stopped here and this might have two further solutions. this has two more sub problems. So what this sub problem is indicating you? So when I am here I4, you have to solve whether to include I4 or not. If you include I4, what will be the M here? Minus W4, and profit will be P1 plus P2 plus P4. So this denotes that combination here, right? And here you are excluding, so the weight remains same. C minus W1, W2 and P1 plus P2. So no element to consider. Here there is no element to consider, so you will end up here at this point. So I hope you understood this, what exactly I am trying to solve here. Okay, so likewise this has its own tree, likewise this has its own tree. For example, this branch, this denotes inclusion of all items in my solution vector. I could have one such problem where I might decide to exclude all such problem. For example, if I have this, so here this too has two more solutions to it. What is that? So I might, if I take left side, what this indicates? This indicates including, and this includes excluding the element. So if I include I2, the next problem will be to solve with items I3 and I4 to be processed. What will be this? Include I2. I2 means W2. Profit will be P2. And if I exclude here, problem becomes, sub problem to solve is I3, I4, and C will be same and P will be same because I have excluded I1, I have excluded I2, and I am this one. For example, if I further decide to solve for this problem, this will have two more sub problems. This is it, and one more sub problems which results because of the choice I make whether to include or exclude. So if I further take another solution to this, I get this from. Okay, so here if you include I3, I4, what is the next problem remaining? You have included here in this side. The next problem to solve will be with I4 as one element to be processed. Since you have included I3, you have to subtract the weight of I3 from the remaining side. The profit becomes P3 since you have included I3 here. And here this still remains as a problem where you have to make a decision for I4 with sack capacity as C and profit as 0. And this will have two more further sub problems. This is one and this is one. So if this has two decisions, decision 1 whether to include, decision 2 ignore. If I include I4, is there any items to be processed? No. And sack capacity will be M is equal to C minus W4, P is equal to profit. And here if I decide not to include I4, what will be sack capacity? This, and profit I end up will be 0. So that's how this works. So here every node has two possible decision sequence. So on, how many nodes I'll have here in the end? Can you guess? I have just solved it for one few select branches. If I solve it for each node till I reach to the end, how many nodes I will have at this at the what I call it, leaf level? Can you guess? Yeah, so almost 16. So if you consider here as 16, what is my input? 4. So is there any relation here? 4 and 16? Yeah, you can almost take it as 2 to the power of 16. So the number of sub problems we are solving here, so actual sub problems appear at this position. So the number of sub problems you are solving are in the 2 to the power of n. So if you recall our complexity decisions, this approach, what is the approach which I have right now, this almost has a complexity of, can you tell me what's the complexity of O of this approach? So we call it as brute force approach, where we try all the combinations. This same approach is further optimized, but you won't have some different approach. All optimized approach are exactly same. We have to still stick to the same recursion tree, the same decision of yes no and yes no, but we keep on optimizing so that complexity reduces. So the time complexity of this approach, what is this? Can you guess what the time complexity of this approach? O 2 to the power of n. This will be the time complexity of this approach. And what we call this approach as? We call this approach as exponential approach. The same exponential approach, what is the approach which we saw here, it can be optimized to a complexity of O to the power of n into c. Right? What is n? N is the size of input and c is the capacity. Right? Remember, you cannot write this n into c as O of n. Remember, here c is also one input here. So the further to approach after optimization. So further optimization, and this optimization is what we call it as dynamic programming. So there are two methods to optimize it. One called as top-down approach, another called as bottom-up approach. And whatever approach which we right now saw, it is actually a top-down approach based on recursion. So after applying that, we get a complexity of O of n into c. Is it better than O of 2 to the power of n? Yes, lot better than exponential. Remember, 2 to the power of n exponential means the performance of algorithm decreases very drastically. But O of n square is far more acceptable. So this comes as a polynomial complexity. Right. So polynomial complexity is always preferred over exponential. No matter, this could be n to the power of 10, that's fine, but 2 to the power is never acceptable. It's exponential is worst kind of complexity of this problem. So given this approach, see, we will come back to this way of why it is 2 to the power of n to n 10 to c and that. As of now, roughly based on the logic that for this problem, we are creating a 16 sub problems where we are doing this processing, calculating this profit. We will find best among this, right? So for input of 4, you are doing 16 sub problem calculation, so it is roughly translates to 2 to the power of n. Okay, how exactly it is 2 to the power of n, we will look at that at the end of this all this series of lectures, where you will have a better clarity of the another approach, all approaches. Then we will make an actual calculation to arrive at 2 to the power of n. As of now, just remember that for input of 4 you received 16. Had it been 3, you would have received 8. Had it been 5, you would have received total 32 leaf problems here. So on based on that rough crude logic, we have arrived at this complexity, right? So now, given this tree structure, can you further solve it for these nodes? Can you try to solve it for entire tree nodes? Can you solve it for all other nodes? So as an homework, I will give it to you to draw the entire tree. So I hope you understood that yes no approach. Have you understood that? Let me know in the chat box. If you have understood, I'll proceed to the next. So we will see the entire tree where all these calculations are done. Then based on these calculations, we will write a program. So all our solutions are at leaf. At this leaf, it is my decision in the end, should I consider this solution or discard this? Should I consider this or discard? Consider this or discard? That's my problem in the end. But you have to check for all combinations. because I cannot know what is good, what is, I have to see what if I include one, what if I two and three. But when you're trying to include all this one, here you get some solutions. P is equal to some value, P1, P2, P3 is equal to some value. If the M becomes negative, means this sum of these three is more than the sac capacity. So if it is more than sac capacity, we ignore that. So as per our this tree approach, that's how we apply. But when we actually write a code, we will not even add this. We will not even subtract if it is. See, this is all possible. But when I write my code, I could entirely skip this, or I can entirely ignore some node, because I might write some condition and I might ignore that. Okay, have you understood this approach? Whether to include or not. If you try all combinations of this tree, you will literally end up by for all combinations of I1, I2, I3 and I4. Have you understood this approach? Okay. So what I'll do is I have already calculated this entire tree. So now I will share that tree and just observe how I have constructed all the tree based on whatever we just saw, right? Okay, so this is the tree. So the green node indicates inclusion. The blue default includes exclusion. Just spend few minutes just to analyze this tree. And is this tree correct as per our logic, whatever we have done right now? See, and I feel that to understand it in one go might be a little bit complex, but if you slightly exercise little bit more thought process, you will understand this approach. So let me do one thing. If I select this node, do you see this selection, whatever I have selected? Let me make it as, uh, let me make it this as this. Okay, not this. Let me change its color to this. Do you see this node which I highlighted? Can you tell me what solution vector this node is representing? I want you to write the solution vector 0, 1, 0, 1, 0, 1. What is selected node is representing the solution vector? Can you type it in chat window? Okay. Yes. Yeah. So most of you are getting right answer. Yeah. So it is 0, 1, 0, 1. Why it is 0, 1? The first element I have moved to this node means I have excluded. So I1 is 0. Then I have moved to right side means I2 is 1. And then I have ignored I3. Then I have considered I4. So 0, 1, 0, 1. So that's the solution vector. So if you do that solution vector, it's a combination of P2 plus P4 and C will be in this. So you will almost will be doing the same one. Okay, I hope you understood this. So now I have to convert this into Python program. Do you think this program will be large? No, this program will be far more. It would be not more than even 3 to 4 lines, since we are writing it in recursion. So now when I want to write this program into a recursion, what is more important to me is this equation. So I will write it for this, and every time I write it, my program has to expand this. So it has to keep on expanding this, and after expanding, it has to calculate max of this too. So what happens? My program expands this, my program expands this. Then still I have a scope to expand this, I will keep on expanding. Then I'll then just start combining them, whatever the max I get in my recursive backtracking one. So when I just keep on expanding everything, then when my function just starts returning from recursion calls, I will just keep on adding this element. Instead of calling adding, I'll keep on accumulating the max of each calls. So when I come back to this max function back, I will be having the maximum profit which I have for this problem. Okay, so let us try to solve this. So what we will do is we will call this function recursively. Do you see a scope for recursion? Yes. So you are continuously calling this max 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 this method, so that you will recursively generate this entire tree problem. So you have a problem to solve. This problem will create two problems, one with this and one with this. Then recursively, so if you look at recursion, this will call this will call this will call this, and this will call this. Then you will call this sub problem. Then you have to compare this two. You have to get the max of this two. Then you get here. Then you solve this two. You get a max of this two. Then you solve this entire sub. You get max of this two. Then you solve this entire this sub problem. Then you get max of this two. And when you come back here, after calling all the recursion trees, then here you end up with the maximum profit. Okay, so shall we move to convert that into code? Yes. So let me open my PyCharm window. See, and while writing this PyCharm window, just make sure, let me know if you see my screen. Okay, do you see my screen? I think this is my earlier program which we wrote. So you can even try to run the program on this. You will get I think you will only get that answer of 17, but you will not get the actual profit of 22. Let me know if you can see the screen PyCharm window. So I'll create a new Python program. So I want new Python file, and let us call it as 01 knapsack. Okay, so I have a 01 knapsack. So let us write our program. First, what we need a list to store my inputs. What are inputs? Can you tell me what is a list? 4 items. What was I1? I1 was 1 comma 1. So how we will represent these items? We will represent this item as list of lists of this form. So P comma W, first element is profit and second element is the weight associated. So P comma W, that's how we will represent this. So 1 1, what is the next element? What is I2? I don't want to switch the window, because if I change this, can someone type this? What was I1 1? I think one was I think here it was, I can see it was 3, another was 16 by, other was 16 and 5, I guess. I don't know. What was I2? Okay, 6 2. Okay. 1 1 6 2 10 3 16 5. 10 3 and 16.5. I hope 16.5 is right. Okay, so I have this, and I have M. What is my here? So generally I have M denotes max knapsack capacity. So in our one it was C in my tree problem. So here what is that I'm solving for? 7, right? I think the problem which we saw at the start of lecture, M is equal to 7, right? And what else? And then I have, okay, I think this is the only two global inputs which I require. So now I need to write a program. Let us call it as max profit. Okay, so to this, what was I providing? This requires my list, and what it requires the capacity, and what else it requires? See, profit is something we will return it, so we will not. So every time I pass the items, every time I call that, if you look at the tree, in tree what is changing is the capacity. So every time I create a sub problem, the capacity for which the sub problem needs to find solution might be different based on whether the sub problem was created by including some element or excluding some element. So I need to provide capacity to this. And let us do one thing. Since we are moving from I1 to I5, we will provide something called as index. This indicates from where I am processing that. So if I'm done with processing all elements, then I will stop my program, right? So if it is a recursive program, for any recursive program, the most important thing is to find the base case, or the case or the input at which my program has to stop, or the smallest possible input my recursive program has to process. So what should be the break case or base case here? When would my program stop? When I get any call with capacity as 0, right? Yes. So if I get some anything with capacity less than 0 or 0, I stop it. Or I might reach to an index beyond I4. So if I talk it in terms of Python array language, so it would be 0, 1, 2, and 3. If I get 4, I need to stop, right? So what I'll do is, if capacity is less than or equal to 0, or if I process all the inputs. How do I know if I processed all the inputs? Index is less than, no, what I say, index is greater or equal to total length of this input. What is my total length of input? I can calculate it by length of items. If this is the case, what should I do? What will be profit if I exceed the capacity, or if I have no elements to process? What will be profit? Profit will be 0. Okay, so if I come to this point here, I'll be breaking my recursion. If it is not the case, let us suppose if I do not get this, if means that, then I have two possibilities. Remember, if it is not the case, I have two possibilities. First possibility is call the element by including it, call the element by excluding it, get the profit of both the calls, and whatever is maximum among the, return it. So if I return the maximum of this, I'm doing the exact process what I have done in that tree process. So what should I do? So here I'll check if. So now I need to check if I want to include element or exclude element. When will I include the element? If capacity, if the current capacity with which I am being called is less than or equal to whatever element I have at this index, right? The first index which I have. If the capacity is less than or items of index, whatever it index item I have, if the weight of that, what is weight? first it's the second element, so I should write 1. If it is the case, the current capacity is, should I write less or greater? I think this should be, current capacity should be, I think it should be greater than, or if it is greater than the current items, the one which is being pointed by index, if it is greater than current items index, then I can include this element, right? So if I include this item, if I include this item, then what will be the next call here? If I include this item, next call will be max profit. If I include this element, what is the next call? I will pass this elements as it is. And will there be change in a capacity if I include this item? Yes. Capacity, new capacity will be earlier capacity minus this, right? The weight of this. And the next element to be processed will be beyond that, index plus 1. Right? This will be it. So once this is solved, I will get some value here. Let me create two profit variables. Profit, let me call profit item included, and let me create one more variable, profit item excluded. Okay, if I include these two elements, I can say here, so this will be profit item included, right? If the capacity is that. If it is false, if this is false, if the current capacity is less than the current item's weight, means I cannot include that item in my this one, because my sack capacity doesn't permit me to include that item. So what's the only solution I have? Ignore that and move to the next element. So the next element, so which will be else part of this if. So if it is not, okay, so only if I have this, I'll get this one. If I include that, if I do not include, then I need to directly call for the next element. So in that case, what will be called? Max profit. The same items to process, capacity remains same, and the index will extend by 1. Okay, and this I will include in a profit of item excluded. So this was your base case. Here you will check if I can include this. If you can include, then you will get some profit. If you cannot include, the only profit you will get it from that, the second element, by excluding that. So there might be a case where you can include this as well. You are also interested to calculate the profit by excluding that. We cannot say that you can have it include and you can ignore it later on. We have to find both the combinations. So if I can include that, calculate this profit. If I can exclude that, calculate this. And in the end, what you have to return here, you have to return max of this. So I'll use the Python function to return max of profit by including item and profit by excluding item. I think this should be the program. Let me see why it is flagging this as warning here. Variable function should be okay. That's fine. So capacity less index greater than length items return 0. Then this is a base case, and these are the max of, that's what I'm looking at. So max profit, profit item excluded, and this one. Okay. Anything else we have left with? So let us do one thing. Let us run that. So at least I feel that we have written all the cases here. Let us run this and see what output I get. Okay. So once I'm done, I have to call this. How do I call? So let me call it directly. Print. Uh, I'll call this one. So now I have to call this. How do I call? Pass the items. Items is global one. What is capacity? Capacity is M. And what is the index with which my processing starts with? 0. So it's a call to recursive method. So here I'll write a comment. Check if we can include the current element. So how do I denoting the current element? By indexing. Check if the current element, let us call current item, can be included or not. So this is what it is. Calculate profit if item is included. And here this is for calculate profit if item is excluded. Since we have to find all the combinations like 0, 1, 0, 1, 0, 1 based on the just recall the tree which we had solved. Excluded. And once this is done, check which profit is max. The one after including or the one after excluding, and return the max profit or price. In our one, we might also call it as price as well. Sometimes we can call it as price. Okay, so let us run. I think okay, so Akash has a question. We should pass profit to function. Why do we need to pass profit? Because see, because these are two inner variables and I'm returning the value. Since I'm returning the value, I don't think I need to pass the profit. Let us do one thing. Let us execute this and let us see what output we are getting. Is my recursive call returning the right profit or not? That's what I have to verify. If I get that profit, let us execute it. Okay. So you have asked me why shouldn't I pass profit? Okay, see, if you think on the approach which we saw in the tree fashion, in the end I had to check whether it is not, but that in the whatever the checks I'm doing here itself. I'm not even including the element into that so the solution vector. So I'm excluding here itself, and I'm also checking if I include it or not. So if I'm able to do that here in code itself, then I don't think that in the end I need to calculate sum of all weights and then check whether I can include that or not, whether I can find out this. So actually the code which I wrote, this code ignores a lot of redundant calls in that. Okay, so let me execute and see what will be output. 0 knapsack. Okay, I get answer as 0. Am I running the exact program? Yes. So if it is 0 means something I am missing here. Okay, here it is written 0. Okay, yes, I got my why I'm getting 0. Okay, See, something is wrong at this line number 13. Can you guess what is wrong at line number 13? I'm getting answer here 0 because I missed something at line number 13. Or else that's why whatever the call I'm doing, it is just calculating 0, 0, 0, 0 and 0 only. I missed something here. Can you guess? I missed at line number 13. See, if I include the element, what will be the profit? How do I calculate? How do I compare two max? So let me see if you can get the solution. So let me see if you can get the answer. Okay, can you tell me what I missed here? Look at this one. I missed something in my code which is not as per this. Yeah, so I failed to include the profit I'll get by including that, right? If you check the question, I have only called this. So what is this including? This is denoting profit with inclusion. This will denote profit with exclusion. So here I failed to add this, right? If I'm including that, I need to calculate that. I was subtracting the weight, but I didn't count this P1 addition, right? Yeah, so to get this, I need to modify the code. Let me go back to window. Yes, what should I add here? I need to add the profit. Calculate the profit if its item is included. So I need to calculate, how do I calculate the profit? From the current item, which is at index pointed by index, from this I need to calculate profit. What is profit? It is 0. Items window of 0. I think this should now solve the problem. So earlier I got 0. Now if it all works, I should get some value. Yeah, did I get the answer? Yes. So you can see here that I have 22. Okay, so now something little tricky, but it will help you later on. So remember, here in Python we have a package called as recursion visualizer, where you can get a diagram which represent entire this recursive call for what items at what value you want to find out the recursive calls for this. If you want to find out recursive call for this, you need not trace it with pen and pencil. Remember, you can generate in your code itself. I'll show you later on, you can adapt that. So we use a small module here, and I'll share a link where how to use that, so you can try it for various other one. So I need to import module OS, and I need to import something called as from visualizer. I hope you know this way of syntax. I think this was taught to you in Python. So when I say import OS, it imports all the modules and packages within that. But if I want to specifically use something within that, I can always write this from visualizer. So it is a package which I've installed. Later on, I'll share the URL from where you will get how to get this in your. So here, that's how I'm importing this. And once I'm importing this, see, do you know keyword functions? In Python, do you know keyword functions? Let me know if it was taught to you or not. If not, I'll teach you in next lecture, but I'll just modify the code as per that. In Python, remember, I can always pass the function by using this arguments as a keyword itself. So what I'll do is I'll quickly write, this is called as decorators. So this has a decorator. Let me see if I can get this decorator for you. So if we can generate the recursion tree, that would help a lot. So this should, okay. Oh, I think it. So these are called as decorators in that. Later we'll come to know. This is an advanced Python syntax. So what I'm trying to do is I'm trying to generate a recursion tree. So if I want to generate a recursion tree, wherever I call this one, I need to call it as a keywords like items is equal to. So this is the same function argument which I'm calling. So Python lets me do this. And index. So actually whatever is being passed, I'm calling this index so that I can plot it in a diagram. That's what I am trying to do this equal to. Just write the argument name in front of that and say is equal to. This is one call, right? This is not the call. Wherever, whatever the function you want to trace, make it as keyword call to it. If keyword was not taught, I will teach you in next lecture. Okay. So once I have, then vs dot make animation, and we can just make the animation here. I'll get a GIF where I can do that, and I can take a delay. So you'll get a GIF image with a delay of 2. Okay, if this is the case, let me execute it again. Okay, if I run, this will generate a recursion tree. What it is saying is 0 1 0 1. Maybe it failed to get that. So here you have to set path for this one. OS dot environment. It's a line. Let me see. I think I have the software installed in some different directory. You need this. So this is where I have that small program which generates this recursion tree into an image format. So I'm just setting that. You will get an idea once I share that link to generate this. So you have to use this code. I'm getting error is probably to not finding that command. Let me execute it again. Okay, so it is taking time. Okay, now it is writing here. So what this will do is it will generate all the images for this recursion, and probably it will generate this image. Let me open Explorer here. And see, just a minute, I will share my entire desktop so you can see. Okay, so when this was done, you can now directly go to the Explorer You have the zero on Knapsack. It generates two files, one with recursion tree and one with GIF. If you show this, it generates the same recursion tree as a GIF image. I think you can't find this. Let me do. I'll open this PNG. Okay, so this will generate that recursion tree, whatever the program I had. So the first call, remember, whatever you have below is the return value of this method. So if you look at here, how my recursion has worked, first one, this, it had two calls, right? One which including and one which excluding. Okay. So this was at index 0. This one will be index 1. So index 1 means 6, 2. So remember, this is return value. Don't think about this value as of now. So this value might have called this one. This will call this function. I hope you can see that capacity is reducing as and when I include this. And this calls this element. So it is just a redundant call, the last call. Okay. So when you get this, so it has written 0. It means that why it has written 0? What is the element which is being processed at? It has exceeded the all that elements, right? So index is 4. And do I have index? No. So this, you have reached the base case. It has written 0. So it is written 0. You have come here, and when you have come here, what you have? Index 3, capacity 1. What is in element index 3? 16 and 5. Can I include this element? I cannot, right? If I cannot include this element, I get what are the max profit which I exclude from that. Exclude from the call from this is this. So the same value, the max of 0 and 0, it is 0. So here too the same happens with excluding that. Now I hope you're getting the tree values. So one with inclusion and one without inclusion. So if you say if the element under consideration, this is you're talking about index 2. So if you include, the capacity becomes 1. If you exclude, the capacity becomes 4. If capacity is 4, then can you include this element? Still you cannot include. So what is the maximum profit you get from this? The profit, the maximum profit you get is by including this element. So if you include, you will get this profit 10. That's what you get. This method is written 10. So the recursion call comes here, then it calls it here. When it goes back, when we are just going back of recursion calls, you are comparing max of this two. So max with including, max with excluding. So this method will return 10. Likewise, this will call. So you can see it will generate entire recursion tree for all these nodes. So somewhere you should, okay, here I have 22. So when you're returning back, you will get value 22. So 16, 22, and the max is what you get this. So what are the values which I passed? The same values go to this method tree as well. So if you want to see it in animation, then you have to open this GIF. But I'm not sure here, the GIF is not in a proper one. I need to expand this. You can see how the recursion calls are being traced. This, then this, and then it returns back and the call starts from here. Okay, so what I'll do is I'll share you this program. You can then start working on this. So okay, can we try it for some other program? Let us just verify if my program is correct. Can you get some another input, sample input for this 0 and knapsack? Can anyone get a sample input for the 0 and knapsack? You might search on internet somewhere. You can take a sample and you can give me that sample. We can execute it here. So let me do one thing. For time being, I will eliminate all this. I think this might be confusing for you, the way we have generated all this P and that. I just for I'll go back to my original program. So this is my original program. Whatever I did, it was just for that purpose of generating recursion tree. Okay, I think it's almost continuously 2 hours we are executing. Okay, Akash has given me some input. Let me first paste it here. Then you can let us try it for that. See, what is that input you have given to me? Okay. What you said, 40, 100, 40, 100. I think I need to change this values here. I'll put this. I'll put it here. What is the first element? Okay, what is this? What is this? Okay, you are given values. Values means profit. W2 means weight, right? So the okay, so 40, 20. Just let me know if I'm right, if I'm interpreting your input correctly. 100 and weight is 10. What is it? It's 50 and weight is 40. What is the other input? Profit is 60, weight is 30. What is sack capacity? What is M? What is sack capacity? I think you have just given me weights. What is sack capacity? Sack capacity is 60. Okay. Then this should be okay. What should be the profit for this, Max? Okay, optimal 200. Let us execute and see. Okay, am I getting 200? Yes. Is 200 the right answer? Sack capacity 60 means, can I include 100? Okay, 10, if I include this, sack capacity is 50. Then it makes sense to include this one. Okay. Yes, it should work for 200. You want to trace recursion call for this? You can do that as well. I've just removed it because see, if you don't know that, unnecessarily writing complex code will just it will increase. You will find it very difficult to do that. But it's not that. I'll share the program with all that one. You can experiment with that. So you can try it with a lot of recursive programs. You will get the recursion call trees and all that. Okay. So I hope you have understood this program. Remember, this is not the end of solution. Now this approach will have optimizations, and during that optimizations we will learn what is dynamic programming. So in short, what we have as of now we have done is called as top-down approach to solve this problem. And whatever the approach which we see, it's a dynamic programming. And in next lecture we will see why I am calling this approach as a dynamic programming problem. See, most of you while looking at tree, you might confuse this approach with divide and conquer, because in divide and conquer too we start all the trees, and while combining, see, if you look at this, you might almost think like I am dividing problems into sub problems and merging that. It is very well, it's not wrong to think in that way, but we will find out in coming lectures why this approach is not a divide and conquer when it looks like divide and conquer. What is that in dynamic programming which misses in divide and conquer, and why do I specifically call it a dynamic programming? Okay, till now we have not yet understood the entire dynamic programming. We have just seen first fundamental approach in dynamic programming to solve zero and knapsack, and the approach which I adopted for this is called as top-down approach. Why do I call it as top-down approach? I call this approach as a top-down approach because the approach which I have right now is a top-down. So your solution starts building from top. From here you are trying to solve and you are getting a solution. There is another approach where you will start from below. You will start from bottom and you start building the solution. That is called as bottom up approach. And that bottom up approach does not require recursion. It can be solved by writing iterative code, but it requires you to keep a specific additional space called as table, DP table. We call it the dynamic programming table. And we start writing our algorithm based on that value. But that approach will only make you sense if you understand this recursion and how we going to optimize this recursion. Once you understand that, the next approach, bottom up approach, is very easy to understand. If you look at various other videos, other literature on this problem, you can now explore zero and knapsack on internet. There are a lot of videos which will explain you how to solve zero and knapsack on internet. All those videos, they directly start with bottom up approach. You will not understand what they're explaining. They will teach you how to by heart this approach. Don't by heart this approach. Understand this approach and write it into code. If you look at those videos, you will almost end up by hearting that approach. By hearting approach will not help you. You understand this tree and recursion approach, rest every dynamic problem is very easy. So we have 6 problems based on zero and knapsack. You will understand how easy it is to solve those problems if you understand this tree structure. Okay, so I think it's almost 2 hours I have continuously engaged. I'll stop at this point. We will see whatever it is on next lecture. In the next lecture, probably I'll spend next lecture on Python and some of this approach. What do you want? Do you want me to continue this design analysis lectures, or you want to continue with Python? I hope as per new timetable, I have 2 Python lectures. So I'll do one thing. I'll share that in Telegram. I'll create a poll and let us decide what to continue in the next lecture. Should we continue the same problem, or should we start learning some Python related thing? And anyhow, I'm writing Python code, so we'll be learning side by side. So I think I'm done from my side. Just let me know, have you understood it or not? I'm not expecting that all 70 should understand, because it might be complex at very first stage. But I'm looking, if some of you have already, if you understood this, I'll be sharing this recording on YouTube. Go through it, watch it multiple times before our next lecture. You will understand. Somehow you will understand that. I'll also share the code with you. So can you respond whether have you understood it or not? Okay. Same, yes. Yeah. Watch it and try to code this problem exactly same by without looking at this. You will get a better way of this. See, this is the fundamental of dynamic. You crack this, dynamic programming is a easy cakewalk for you. Okay, so I'm happy that some of you have responded yes. Okay, fine. So I'm done from my side. Thank you for patiently attending this. It was a very long 2 hours lecture, but this is required. I cannot break this lecture into true and that. So I think I'm done from my side. Thank you for attending this. I'll share the recording on YouTube and I'll share the URL with you. Thank you.